Good afternoon, everyone. As you remember in last class, we discussed polymer chains and how they form through polymerization, where you start with a monomer. In this case, we can look at ethylene gas. And through a radical polymerization, this double bond opens up. But we're not going to go through that again, but you remember the initiation step where the double bond opens into a radical, the propagation step, and then the termination step. And that eventually turns into polyethylene. Where N is the number of repeat units or monomers in the polymer chain. So we learned how these polymers formed and what kind of equations dictate the chemistry, the rate of formation, as well as the number of repeat units in a given set of conditions. What we didn't talk about was what kind of global chain formation the polymer takes once it turns into a polymer. And what we're going to look at is going to be a very idealized case where the polymer can flex in any conformation at once. And what's going to be interesting is we can do this completely statistically, just by using what's used a lot in particle physics, what's termed as a random walk. So basically a random walk is if we're in one-dimensional space, this being 0, 1, 2, -1, and -2. If we start at the point 0 origin right here, if this particle were to move randomly, the step size being one jump, it'd either go to the right or to the left in one jump. And the random walk would basically be, it can either jump here or here, it has an equal probability to do so, and then after that it might jump back to 0 or jump to the 2 position. And this is basically what a random walk is, and this basic concept can be applied to three-dimensional space to describe how a polymer chain folds into a conformation. So in the case of a polymer chain, we'd start at some type of origin point, and then the polymer would take a step size that's equal to the bond length of one monomer, L. So it'd take one step, and then another, and then another, and another, and another, and another, and so on and so forth. And we can term each one of these steps by just vectors. So the first one could be, for example, the R1 vector, and then R2 vector, the R2 vector, and so on and so forth until the last one where you have the Rn step vector. And then to get the global chain conformation, or the end-to-end distance, or the radius of the polymer chain, you just need to have this vector here, from the first step vector to the last step vector, which would be just R. And this, of course, would be the sum of all of the step vectors. Once again, where N is the number of steps or monomers in the polymer chain. Now, of course, if we wanted to get a general idea of the average polymer chain radius that you would see for a given molecular weight, we could take the average of all cases. But if we did this, we would get 0. Because if I were to step this way, I have an equal chance of stepping back. If you take the average of all the cases, you'll have 0. So the simplest way to get a non-zero average is to take the mean square end-to-end distance. So we simply just have to take this equation and take the average of it and square it. And this, of course, can be rewritten as a double sum. Of the step vectors Ri dotted with Rj. Then these two values, I and j, just being step vectors in the same polymer chain. Now, we know that these step vectors are equal to the bond length L. So what we can do is that we can go ahead and equate the absolute value of each I step vector is equal to the absolute value of each j step vector, which is equal to the bond length, L. Under this assumption, then we can then say that if you were to take the dot product of any step vector I and any step vector j, it would be equal to the magnitude of them squared, which is L squared, times the cosine of the angle between them, cosine theta of I and j. So this then leaves us with the radius of the polymer, the average radius of the polymer squared is equal to L squared, or the bond length squared, times the double sum of the angle between step vectors I and j. Now, from here, there are many different situations for this angle cosine theta. And the biggest thing we can take away from this is that since we're taking the average case of all angles that could occur between step vectors I and j, any case where I is not equal to j would then average to 0. So any case where I is equal to j, or where I does not equal j, cosine of the angle between them equals 0, because it averages to this case. However, if I is equal to j, then the angle between them is 0, so the average cosine between them is always going to be equal to 1. And since there'll be n cases where I is equal to j, because they're part of the same step vector, we can simply simplify this cosine theta term, or the double sum of it, to simply n. So by doing the simplification, we have an equation that only involves the bond length and the number of steps taken. And if we actually want to get the end-to-end distance, or r, we just have to take the square root of both sides. And that's just equal to n to the 1/2 times L. And this is a very important equation. This is termed as the freely jointed model of a polymer chain in space. And basically this is important because we can see that in any case L is going to be constant for any given polymer chain. What will change is the number of steps, or the number of monomers, or the molecular weight of the polymer chain. But this will always scale by proportionality of n to the 1/2. That's a very important property, and a lot of polymers follow this property, or systems very similar to this one. Now what's interesting is that you can actually model this very easily in MATLAB, which I'll be having you guys do in the homework later this week. But basically, if you have a MATLAB program that picks a certain origin point and takes steps away from this origin point, and these step sizes are equal to the bond length, you can have it do it. In this case, I had to do 1,000 steps, and you can run it, and you'll see the polymer chain that forms to these step sizes. Now what's really cool is that you can then get the end-to-end distance through MATLAB, and you'll find that it's actually pretty close to the theoretical one. So this first one that says Rn is the one that MATLAB calculated by actually taking the vector from the first step to the final step, whereas Rn theoretical is equal to 31.6, which is this equation we just derived right here, n to the 1/2 times the bond length. So you can see that this is a very good way of approximating the polymer chain, and it can be simulated very easily statistically using a Monte Carlo simulation. Now of course, this is a very idealized case of a polymer chain. Polymer chains do not actually behave this way. In fact, this is much smaller This is much smaller than a polymer chain that you'd see in reality. And the reason for this is that there are many other restrictions we need to take into consideration. And we'll get into this next class. But to give you a general preview, when you have a carbon-carbon bond, it's not going to exist at any bond angle. It's going to happen at a very specific bond angle. As many of you know, the tetrahedral bond angle, which would be, I believe, 109 degrees. So that means when one takes these step sizes, they're always going to happen at an angle termed theta of 109 degrees. So that's a major restriction on this model, and that would cause the chain that we just did in that lab to expand, of course, because there's so many restrictions in three-dimensional space. And then finally, as you know, this carbon bond can, of course, rotate around its axis, but there are only certain rotations that it can perform. Some of them are energetically forbidden, some of them are energetically favorable. So if we include a Boltzmann distribution into the steps that are taken by the polymer chain, this will further restrict what steps are allowed and which steps are forbidden, as it is folding in three-dimensional space, which will further expand the chain. And we'll get into how to incorporate it into this equation next class. So read chapter 3 of the book, and I'll see you guys next Thursday.